Swayam Prabha. Digital India. Educated India.
So after understanding the Kirchhoff's voltage law and Kirchhoff's current law, let us consider the example where the following circuit. So we have a source. If it's a DC source, we can represent this way, and then we have a resistance, and then we have another resistance. So this is R1 and this is R2. So this is Vs, the source. Okay, so we'll assume the voltage drop across this is V1 and voltage drop across this is V2, assuming the current of the direction is this. Since both the elements, both the resistor are in series, the current will be same. So assume the current is I. So the voltage drop across R1 will be I into R1. Similarly, the voltage drop across R2 how much it will be? I into R2. And what KVL says? In a closed loop, sum of all the voltages is 0. It means the voltage, so this is basically the algebraic sum. So source, if we start from this point, the source is rising, so positive, minus there is a drop, minus there is a drop, equal to 0. So it means that the total voltage V is nothing but the V1 plus V2. Okay. Now if we like to solve this, so the voltage V is nothing but I into R1 plus I into R2, which is nothing but I times of R1 plus R2 into V. So this is nothing but the equivalent resistance. So V I and this is R equivalent. This is the representing the circuit. So it means that the R equivalent is nothing but the R1 plus R2. Okay, R1 plus R2. So we can write a statement that whenever just recall it, when a number of resistors are connected in series, the equivalent resistance is a sum of all the resistance. So for example, we'll consider the following circuit. We have a circuit in which there are two resistors connected in parallel. So how can we see that it is in parallel? Because they share the same node. point A and N. They are sharing the same node, so they are considered it. So the voltage across the register RESI, sorry, the voltage across the register R1 and R2 is R2 are same. So what is that voltage across R1 R2? Is nothing but the voltage V. So the V across R1 is V and V across R2 is V. This is plus minus V1 and this is plus minus V2. And the current which is coming here is I. Out of that, I1 is going here and I2 is going here. Now using Ohm's law, we can say that V1 is nothing but the I1 times of R1. The voltage across R1 is, which is appearing V1, is nothing but the product of I1 plus R1, I1 into R1. Similarly, V2 is nothing but I2 into R2. This is nothing but using Ohm's law. Okay. Now keeping this in mind, apply KCL at node A. So node A, the incoming current is I, minus I2 is leaving the node, minus I1 is leaving the node, and the total sum will be 0. So I is nothing but the I1 plus I2. So add these two current, which will be equivalent to the total current I. So I is nothing but, so putting the value of I1 I2 from this equation. Okay, so this will be V by R1 plus V by R2. Correct. So here we have put, so suppose this is 1 and this is 2, or we can just erase this part. Okay, we just erase this part. So V1 and V2. So putting the values from 1 and 2. So this becomes V times of 1 by R1 plus 1 by R2. If we can compare with the equivalent resistance, this is nothing but the 1 by R equivalent. So in terms of Ohm's law comparing, so I is nothing but V by R equivalent. Okay, so here R equivalent is nothing but the 1 by R1 plus 1 by R2. Now let us develop some understanding about the capacitor. Okay. Capacitor is a passive element which is designed to store the electrostatic energy. Capacitor is also very commonly used electrical component. Capacitor basically consists of two metal parts which are separated by a distance d. So suppose there is a plate, two identical plates which are separated by a distance d, having a surface area s. Okay. So if I make like a look like a plate, then this is the, it is connected, and the voltage, suppose this is the connected to the ground, so this is a symbol for ground, and this is connected to the voltage V. So when this is the voltage V and there is a gap, so charges will not get to transfer here, and it will get charged to this. So whenever it is charged to suppose positive volts, it will get positively charged. and due to the attraction, the negative charge will start appearing in lower bottom plate. So total charge Q here, and the Q amount of negative and Q amount of positive charge will be there. So when a voltage V is connected across the capacitor, the positive charge and the negative charge, the polarity will be different on the opposite plates, but the amount or magnitude will be same, and that amount of charge Q is nothing but the proportional to the voltage. Okay, so the charge Q is nothing but CV, where C is a proportionality constant, which is a capacitance. So we can write C as a Q by V. So here we can define the definition of capacitor. So capacitance, the ratio of the charge on the conducting plate of a capacitor, basically. Okay, plate of a capacitor, conducting plate of a capacitor to the voltage applied across it. So the C is here the capacitance, is measured in the capacitance, which is measured in farad, represented by. Okay, so 1 farad basically, so from here you can see 1 farad basically 1 coulomb per volt. So 1 farad basically 1 coulomb per volt. Okay, so it means that when you are charging a capacitor with a 1 coulomb charge and applying a voltage of 1 volt, that means the capacitance of that unit of charge which is holding is 1 farad. So we can also define the capacitance in terms of the dimension of this capacitor. So when we can define the capacitance of in terms of dimension, C is nothing but the epsilon A by T, where epsilon naught is nothing but the permittivity of the medium. So the medium is basically between the plate. Okay, so permittivity is nothing but the dielectric material which is being inserted between the plate. So here if it is air, for epsilon naught for air is nothing but 8.854 into 10 to the power minus 12, and A is the area of the plate, and D is the gap between the positive and the negative plate, and two plate of capacitor. So gap between the two plates. Fine. So the unit forgot to mention here, it is farad per meter. Capacitance from the formula epsilon naught A by D. So from here we just observe few things. If area is high, which means that what will happen? The capacitance is going to be large, and if gap distance is increased, then the capacitance is going to reduce, which is like inversely proportional. Correct? And this is directly proportional. Sorry. Now further, if the epsilon naught is replaced by some other epsilon, not epsilon r, where epsilon is relative permittivity. So if high dielectric constant material is inserted between the plate, then also C will increase, the capacitance will increase. So these are, so between the capacitor, it is identical capacitor and applied voltage V. Similarly, one more capacitor is there, identical, and where applied the voltage is V. But here the epsilon is nothing but the epsilon naught in R. Epsilon is nothing but epsilon. So here it is only air gap. It is dielectric material with a permittivity of R. The capacitance will be higher in this case. So there is a material and it is air. So in this way the capacitance can be increased. So in the electrical circuit, the capacitor is represented by two parallel plates in this. This is the representation of a capacitor. This is a constant value. Okay. Is charged with a voltage V. The current is flowing, and if the capacitance is varying, so it is a variable thing. Capacitance, charge voltage is, so this is basically a variable capacitor representation where this arrow represents the variability. So to obtain the current voltage relationship, we take the derivation of the both sides. So Q is equal to CV. This is the equation from earlier expression. So derivate with respect to time, we get C dy dt plus V dcy dt. We assume that capacitor is a constant, so this term will not be of any and we can just neglect it. So basically this becomes I. This is nothing but d dy dt. So this is the current passing through the capacitor, IC. So IC, nothing but the current flowing through the capacitor, and V is the voltage across the capacitor, and C is the capacitance assumed to be constant. So this is the current which is flowing through the capacitor. So the voltage and the current relationship, if you want to have the voltage then voltage will be integration of you integrate both sides keeping the voltage as a quantity, then you'll get this expression where Vt naught is nothing but the total charge divided by capacitance at time t naught. So basically the initial condition or the initial charge. Suppose the capacitor is initially charged to some voltage already, and then the additional charge is coming up, then it basically adds up. So the capacitor voltage depending upon the past history or the initial value. So this is the condition for initial value or charged capacitor. If it is initially discharged or non energized, then it will be 0. So suppose we want to have a instantaneous power delivered. Okay, so now if we write the expression for instantaneous power delivered, so we have a instantaneous power P is V into I, and V is nothing but, sorry, I we can replace that C dV by dt, so it is nothing but half CV square integration means this will become the energy. Okay, so this is basically energy stored in the capacitor. So energy stored in the capacitor is half CV square. For initial charge present at the capacitor is 0. So initially uncharged. This capacitor is initially uncharged. The voltage across the capacitor is nothing but 1 by C integral at dt plus initial charge T naught. Now IC was C dV by dt. So this is the capacitor current. So assuming that V is constant, V of t is constant. So what does it mean? It means that the voltage across the capacitor is not varying. So the capacitor is charged to a specific voltage and it's maintaining, there is no current flowing through it because dV by dt will not be present, it will be 0. So IC is equal to 0 when capacitor voltage is not changing. Which means that in the steady state the capacitor will behave as a open circuit. So capacitor will be behaving as this when fully charged or steady state. This is a capacitor which will be behaving this at t equal to infinity. Further, in addition to this, if a DC voltage is applied, if a DC voltage is applied, which also means that the total current 0, or the current flowing through the capacitor is 0. This capacitor current, right? The current is 0. The second condition is the voltage on the capacitor must be continuous. Okay, so voltage across the capacitor is allowed. Okay. So when we have a dV by dt, it always gives a very high spike of current whenever there is a sudden changes in the voltage. So if you have some kind of variation in the capacitor voltage of this type, so suddenly if you see the voltage went to 0, so this is a time, this is a V, and this voltage suddenly when going to 0 means dV by dt is very high, dV by dt is much higher, right? This dV by dt multiplied by the capacitor, the IC current will shoot up very high, and that much high current will go to the other part of the circuit, and it may be very dangerous to the other component. So what is the permissible thing is that whenever there is a capacitor, we should maintain a voltage constant or a smooth variation. We cannot suddenly change the voltage, it will not permit the voltage change, so it holds the voltage. This is what the role of capacitor is. So this is about the capacitor. Now if you see the kind of series and parallel combination, so now series and parallel combination. So suppose there are some capacitors which are connected in series. This is C1, C2, like that. Cn capacitors are connected in series, and you are feeding a voltage V, the current I is going. Okay, so the total voltage V is nothing but V1, V2, V3. So V1, V2, V3, C3. This is polarity. So this is the KVL. Okay, this equation is KVL. Okay, so the voltage is basically capacitor, right? So voltage V is nothing but 1 by C integral IC dt plus V1 at t naught, and V2 will be what? Similarly 1 by C2 integral IC of t dt plus V2 V naught. So when we are calculating, what we are assuming, when all are in series, the current will be same. Capacitors are in series connection, the current is same, which is flowing through the capacitor C1, C2 and Cn. So the current suppose is IC at time t dt, sorry, time t with initial voltages corresponding V naught. Okay, so this is the current. Similarly, you have all the voltages. So we can add. So this will be common. This terms will be, so assuming initially uncharged. So in the common term we will be having 1 by C1 plus 1 by C2 plus 1 by Cn. Then we'll be having integral IC of dt plus C1 at t0 plus C2 at t0 plus Cn at t0. Correct. This can be assumed as some quantity which is Vt0. So when we talk about 1 by C equivalent integral ICT dt plus Vt0. So it means this is equivalent capacitor which is initially charged to this voltage. Okay, so this is total voltage V. So here we can see that the equivalent capacitor when they are connected in series is nothing but this basically represent a single capacitor where V is the applied voltage and Vt0 is the initial charge condition and IC is the current. So this is equivalent circuit. So corresponding to this equation we can write 1 by C equivalent is this. So you can remember what was the condition for the resistor. It was reverse, right? In the parallel combination of the resistor, this something of this kind of formula was observed, where we have 1 by R equivalent is equal to 1 by R1 plus 1 by R2. That was in parallel. So but this is in series connection of capacitors. Correct. Now similarly, if the capacitors are connected in parallel, okay, so now the capacitors are connected in parallel. So you have one C, C2, C3, C1, C2, C3. The voltage is Vt, current is going this one. Current in this one will be I1, I2, I3, and the voltage is for time being this, it will be changing. It is a time dependent voltage, right? So now let us consider the situation where the voltage which is being applied is across the parallel connection of the circuit. So in parallel connection, the total current if you apply, so this is the same node, right? This node is same, because at this point all the capacitors are connected and this is the node, all the points are connected. So applying KCL at this junction, total current, charging current of the IC, which is I C, is nothing but I1, I2, I3, and so on. Correct. So we have all the current I M. So in this particular case, we can simply write like IC is nothing but the C1 dV by dt plus C2 dV by dt plus C3 dV by dt plus C dV by dt. Okay, so this is the thing. Now d by dt is common, so this is like C1 plus C2 plus C3 Cn and d by dt. So this is the kind of general equation which we got by looking at the series connection. So when comparing to the equivalent circuit, IC equal to C equivalent d by dt means it represents some circuit of this curve. Where V you are applying the voltage and IC is here. C equivalent is this. So C equivalent when the capacitor is connected in parallel is C1 plus C2 plus C3 plus Cn. So this is the series connection and parallel connection of capacitor. So we have found out the series and parallel combination of different capacitors. So far we have understand the series and parallel connection of the capacitor. Now consider the inductors. Okay, so inductor is basically represented by a spiral way. This is the representation of inductor with the capital L, and the voltage across this is VL, and the current is flowing I. So this is the circuit representation of the inductor. So the symbol is given here. Now when we talk about the series and parallel combination, so first let us understand the series part. So suppose there are three inductors L1, L2 and L3 are connected in series. So keeping this situation, let us draw a circuit. So we have L1, then we have L2, and then we have L3, and these are connected in series, and the voltage applied is V, current is I. So here you see the voltage across this will be VL1, then it is VL2, then is VL3, L di by dt. Similarly, the V2 is what? L2 di by dt, and then V3 is L3 times of di by dt. Okay, because the current is same in series. So these elements which are connected N1, L2, L2 will see the same current flowing in this direction. So the voltage will be this way, drop. So in this particular case, now apply KVL. If you apply the KVL, the voltage source VL minus VL2 minus VL3, total voltage Vs, so it is nothing but the zero. So this is the equation after applying KVL. Okay. So after applying KVL, so now from here replace the values of all VL1, VL2s and VL3s from this expressions which is written above. So Vs is nothing but L1 di1 by dt plus L2 di by dt. I1 is nothing but the I only. So the current which is flowing through the inductor 1 is nothing but the total current plus L3 di by d3. So the di by dt is common in all, so this will be nothing but L1 plus L2 plus L3 di by dt, it is Vs. So if we write it as Vs as L equivalent di by dt So the circuit that represents this is nothing but a voltage source and the current I, which is going through a single inductor. And the value of that inductor is nothing but L equivalent. So this circuit is basically now represented by this equivalent circuit. Okay. So when we talk about this circuit, the L equivalent is given as L1 plus L2 plus L3. Similarly, if there are n components connected, then the values of L equivalent will be the sum of all the series inductances connected in the circuit. Now look at the parallel connection. So this is a very important finding. Now look at the parallel connection. So when we talk about the parallel connection, let us have a set of 3 inductance, 1, then another one, and then one more. And the across which the voltage applied is Vs. Okay. And the current is, total current is I, but here it is going only I1, here it is I2, and then it is I3 in the inductance of L1, L2, L3. So this is basically L3. So now you can see that the terminal voltage between these 2 points, which is nothing but the across L1, L2, L3 are same. So VL1 is nothing but VL2 is nothing but VL3, which is nothing but Vs. So this is the first look at the parallel circuit, that the voltage across it will be the same. Now using this only, apply KCL at node A. Suppose this is A and this is the same node, right? There is no element connected in this branch, so this is the same node. Here also it is same node. So between A and B, so apply KCL basically at A. So what will happen? The total current is I, which is nothing but I1 plus I2 plus I3, and I1 you can write it di by dt, then nothing but di1 by dt plus di2 by dt plus di3 by dt. This is a derivative, so we have just taken a time derivative both sides. After taking time derivative both sides, okay, so we have taken the time derivative both sides. So di, we have written the expression from here, right? Like v1 is nothing but dl di1 by dt, and v2 is nothing but l di2 by dt, and v3 is nothing but the l3 di3 by dt, and these are same. v1 equal to v2 equal to v3 is vs. So from here, this di1 by dt is nothing but vs by l1. Similarly, di2 by dt is nothing but the vs by l2, and di3 by dt is nothing but vs by l3. So using these 3 expression, just replace here, we get di1 by dt nothing but vs by l1 plus vs by l2 plus vs by l3. So it is nothing but 1 by L equivalent of Vs is nothing but the di by dt. So what is 1 by L equivalent? 1 by L1 plus 1 by L2 plus 1 by L3. So these are the equivalent inductance when the inductor L1, L2 and L3 is connected in parallel.